All right, well, welcome to another example using relative velocity. This time we're going to use trigonometry to solve a problem that I've already shown in our video, an example using x's and y's, x and y components. So this question is number 7 in your handout package. It's the helicopter who has a certain distance they need to travel in a certain time, resulting in a what we call ground speed. So we're given 182 kilometers in 2 hours. The ground speed here is going to be, I think it's 91 kilometers per hour. And you should have seen that in the last video. So we've got a ground speed. The most important thing when we're talking about anything to do with airplanes in this case, that's all essentially everything, every example I can come up with to do with relative velocity, whether it be an airplane or a helicopter or not. But the idea is that ground speed is equal to airspeed plus wind speed, meaning where you end up equals where you aim plus where you are pushed due to an outside source, which is wind. And obviously other types of examples can be water, so like a river pushes you a certain amount, a certain direction, that sort of thing. In this case, though, it's just our helicopter. So that's the fundamental idea of relative velocity. In this question, we are looking for what we call airspeed, which is where the pilot has to aim in order to meet their schedule due to a given wind speed, average wind speed. Just quickly, the equations. This is the basic equation for a relative velocity. I know that the subscripts can be a bit much, but essentially PG is ground speed, airspeed, wind speed. AG stands for air to ground. P to A is plane to air. P to G is plane to ground. This rearranges because we're actually looking for airspeed. So this rearranges to VPA equals VPG takeaway. So all I'm doing is rearranging for VPA. Using what we know we have to do for trigonometry, we don't really subtract using trigonometry. What we do is add a negative. So rewriting it just one more time in terms that we can draw a triangle. We want to draw a triangle. We don't subtract triangles, but we can add in triangles. So we add a negative. Hopefully by now you remember that, well, I guess these are the givens. We'll get to the negative in a minute. So we figured this out in the last example. This is based on having to travel 182 kilometers in 2 hours, works out to 91 kilometers per hour, and the angle stays the same. Here's our wind speed is given in the question, and this is what I was hoping you'd remember, that when you find the negative of a vector, essentially everything stays the same, same, but here, opposites, north to south, north becomes south, east becomes west. So you take the totally opposite direction. So this is the vector, the vectors we're going to use for our vector addition. So let's go ahead. We need to make a triangle here. So remembering that our first triangle, or our first vector, I mean, 91, and that was 17 degrees west of north. And our second vector that we're adding is 38, and it was 25 degrees south. Okay, so I'll try to draw them. It's good if you can take up as much space as you can in the drawing. So if I draw my first vector, 91 kilometers per hour, so that's 17 degrees west of north. So I'm going to draw a little coordinate system right here. And my vector then would be 91, whatever that is, but the thing to make note of right here is an angle of 17 degrees in between sort of my north axis and where my vector is. So from here I add 38 kilometers per hour, 25 degrees south of west. So it's going to be a shorter vector, and it's going to look something like this. So that's going to be 38. This angle right here will be 25 degrees. And my sum, my vector sum, which ends up being PA, what I'm looking for is from where I started drawing to where I finished drawing. And this is what I'm looking for. Okay, so all I have to do is solve this triangle. The information that I've got this couple of degrees here. If I want to find VPA, and I'm going to use cosine law, I need to figure out this angle right there. So what you can do here is you can use the fact that you've got a bit of a Z going on, starting, my Z starts here, so there's 17 degrees coming up, coming up, coming up. This here must be 17 degrees. And the other thing I know about this angle is that I've got right angle right here. So if this is 25, this must be 65, right there, leading to 65 plus 17, which is 82 degrees across with VPA. Now I have enough information to use cosine law. Where VPA squared equals so all I've done is taken the other two sides and cosine the angle across from VPA, and VPA ends up being 93.6. Now if you did the last example with x and y components, you'll find we got exactly the same number. The other thing that we found when we did x and y components is that this angle here was 49 degrees. So we need to show that you can get the same thing using trigonometry. And what will help us do that is, since we know that this angle right here is 17 degrees, if we can find this angle, this is called theta, this angle inside the triangle, theta plus 17, should leave, if I added those up and take away from 90, I should end up with 49 down here. That's the goal. So let's first solve for theta, where sine theta over 38 equals sine of 82 over 96. And if you solve for theta, you will get 24 degrees. I'll leave that for you to do on your own. So once you have 24 here, now we can say that this angle, rather represented by my little dot down here, dot equals 90 minus 17 minus 24 equals 49 degrees. Therefore, I can give a final answer to my question saying that my airspeed is going to be 94 kilometers per hour, 49 degrees north of. Now the nice thing about using trigonometry for these problems is that sort of the check mark is implied. You can see it right away. It makes sense that this is where I aim. This is what I was trying to show at the end of the last question. If I aim here, then the wind is going to push me, because the wind is north and east, not like the picture that's here, but the wind's going to push me up to here, where I want to end up. So I aim, the wind pushes me here, this is what I end up doing. And that's essentially why in relative velocity, it's nicer to use trigonometry than it is x and y components, but x and y components do work just as well. Anyway, maybe practice a couple of those, or just cover this solution, or you wrote down the solution, cover it up and try the question on your own and see if you get the same answer.